moderating the first half of this session. My name is Charlie Weiss, and I'm introducing Dave Vavrinak, who's been working with me for the past about a year now so far on a project on Ramachandran Outliers, data mining and analysis using the Python programming language.
Hello everybody, I'm David Vavrinak, and I'll be presenting my research on Ramachandran Outliers. But before I get too into details, let me start with a bit of background. First, let me describe what a protein is. It's a large biomolecule that consists of a few amino acids, two or more, well, more than two. And they come together in a condensation reaction. You lose some water, and you form a peptide bond. So these proteins are important in vivo for lots of things, including DNA replication, biological catalysis, etc. But I have two amino acids right here. This one is lysine and this one's phenylalanine. Don't worry about that, it's only on the quiz. We have the same backbone, so they each have this nitrogen, carbon, carbon, double bonded to oxygen, and another oxygen. Here, blue, black is carbon, blue is nitrogen, red is oxygen. So those are the same. And then we have this nitrogen, which attacks at the carbonyl. It's just where it wants to attack. And we have a dipeptide from that. So this is now our dipeptide. And then we have a nice little water molecule that forms from that. So, Ramachandran outliers are a way of analyzing these proteins, and we take the psi and phi angles. So psi is in between this and these two carbons here, and then phi is in between the carbon and the nitrogen. So these are dihedral angles, which means planes at which they come together. So in chemistry, big things don't like to be by each other. So we have these two bulky R groups, the only thing different between these two peptide or two amino acids. And big things can be further away from each other or close. When they're close, that's bad. So we plot these, and we see that outliers occur when the big things are close together. Favorable means they are reasonably apart. There's not a lot of steroconnections, and some can be allowed, which is like in between. So why are Ramachandran outliers important? Well, it's because of quality. The WWPDB, which is a biochemistry protein database website, they classify proteins based on their quality of structure and how they were solved. And they use Ramachandran outliers as one of their 4 metrics to assess the quality. So here we have a value of 10.2%, which is way too high for a normal protein. We'd expect less than 1%, fewer than 1% of the amino acids to be outliers. So, I mentioned a PDB file. This is X-ray crystallography data. And what X-ray crystallography allows us to do is construct a 3D model of a protein. And the top 8,000 that we analyzed, those are considered good quality structures. So we'd expect them to have outliers that are actually supposed to be there in nature. Because they do exist, it's just the majority of outliers that we see are caused from missolvings of the X-ray crystallography data, human error. So our goals included data mining these quality top 8,000 PDBs. And we consider them quality because other scientists said so. We look for trends in these data, and we use them to identify errors in lower quality PDBs. So to start with Python, which is what we use to data mine, it's a powerful and prevalent programming language that you can use for simulations, advanced calculations, and I focused on data mining. Coders all around the world use it for mathematical models, protein models, bio, chem, anything you can name, physics even. So the procedure started by writing this script in the Python 3 programming language, which is just the most recent version of Python. And we analyzed it in this environment called Spider. And we stored all of our data in an HDF5 file. Well, an HDF5 file allows us to manage the data bit by bit because our file is 8.6 gigabytes. And if anyone knows something about computers, that usually is exceeding the working memory of a computer. So we just take it piece by piece. The Ramachandran analysis was performed by Phoenix, which is, it tells us whether a residue, which is an amino acid within the protein, it tells us whether that's favorable, allowed, or unfavorable, which is the outlier that we're looking for. And our final script in the Spider environment, that allowed us to compile all this data into what's called a data frame, which I'll show you in a second. And we stored all of these data frames in a Jupyter, or in a HDF5 file, and analyzed it in a Jupyter notebook, and I'll also show you what that is. So this is what Spider gave us. This is just 24 of the amino acids, the residues within one protein. And we have all this data, including the evaluation. These ones happen to mostly be favored. They should mostly be favored. We have one allowed here. Outliers aren't common, so they didn't happen to be in the top 25, the first 25. And then we have outlier phi inside, the dihedral angle as I was talking about. And we have the residue before and residue after, which will come in handy later. So let me show you how we took all of those and analyzed them. So we had 7,960 some of 62, I'll just say the number. We had all those data frames, and why would a person go through those by hand when you have some coding techniques that you can do? So what I just did now is run imports. It just allows me to import whatever I want to use to manipulate the data. Not manipulate in a bad way. We normalized the residue, which means we looked at how many, for example, alanine is one of the amino acids. We looked at how many alanines consisted of the entire representation of outliers. So if we say 7% alanine, that means 7% of all the outliers are alanine. We then went to compare them by what we thought would be a good comparison is size. So we used the IMGT scale, and they basically just take all 20 amino acids and break them down into categories. So we have very small, small, medium, large, very large, pretty creative. And so we took all the residues and classified them into these subsections. And I already ran this, but I want to do it again for dramatic effect. We have outliers versus allowed versus favorable. We then did the same thing, but we went based on polarity. And polarity just means there's a partial difference in charge. So one could be partially positive, one could be partially negative in the R groups. Or charged means one's fully negative or fully positive. So that's what we got for those. And we then did a pair plot, which just takes all the information from the nice pink data frame that we had, and it plots each column by each column. So that could allow us to look at a few trends for all the data analysts in this room. You can see there's no trend at all right there. So we didn't consider that. But there are things that might end up working out as trends. For example, I don't know, you can't read it, but evaluation versus, I have to go back here to check. Evaluation versus the residue before. So that might be something we're interested in looking at, which we will end up doing, but we have not done yet. And then we did 3D IPCA, which is incremental principal component analysis. And that basically just allows us to reduce the dimensions that we had. So take the data frame we had, there were 13 columns. We reduced that into 3, and it looked for trends for us. There's a lot of math involved in that I won't go into, except I can talk to you after. And we got this output. And then we did the same thing, but we reduced it to 2 dimensions because we liked looking at things in 2 dimensions on paper. So, going back, we saw this graph already, and we determined that the most common outliers included proline, and we had glycine here, and then we had serine, and aspartic acid, and valine. So those were our top 5 most common residues. We did the size analysis. So what's interesting here, when you look at outlier, you see very small and small. They consist of 60% of our outliers, but we compared it to favorable mostly. Look at the favorable. When you consider those smaller residues, you only have about 40%. So that's a significant difference. And we reasoned that it might be because a smaller residue, so if I take this is also a valid R group. The smaller ones are easier to move than these bigger ones, is just what we concluded. Though we would have to run that by Dr. Novak or Taylor. And then we looked at polarity or charge. We didn't see really anything significantly different. They're all roughly the same. So, the trends in the IPCA, which is a machine learning algorithm, we saw that the outliers tended to favor the middle of this first principal component. And we just saw that trend. We don't actually know what it means yet. We can look at it. And the 3D principal component analysis, it's just a big cluster, like a ball. It looks cool though. So, to summarize the project, it all started when Dr. Weiss approached me and said, "David, I have a project you might be interested in." And we took that. He showed me what a PDB file is and how we can mine it, and it's actually pretty organized. It's not too difficult to go through these, it's pretty difficult to go through 8,000 of them. And then we created the Python script, so this part here just happens to be the top of what goes through this PDB file and gathers the data for us. Then we analyzed it in Jupyter, the little environment I showed you with all the charts and graphs. And then we used the 3D and 2D IPCA, incremental principal component analysis, as machine learning techniques. And we will further analyze that in the future. So again, we wanted to see, we saw the outliers here. We're pulling toward the middle, but we do want to know, what does that mean? Is that an actual trend, or is it something we already know? So we're looking into that. And we also want to know what the outliers' neighbors say. So we got data from every amino acid within the protein, and we know what comes before it, what comes after it. That could potentially be something to look into. We also want to use machine learning to predict valid outliers versus invalid outliers, which 2 students, Jacob Alanese and Connor Smith, are currently doing. So I would advise you to check out their poster and see if we can find correlations between environment and outliers. So, I would like to acknowledge Dr. Charles Weiss for being my advisor on this project, but not only that, he taught me all the coding I know. And Dr. Walter Novak, who is one of our biochemists, and he helped us break apart this PDB file, understand it. At first glance, it looks like just numbers and letters, but they mean stuff. And Dr. Colin McKinney for explaining some of the mathematical techniques like IPCA. And it's really we call it machine learning, but it's really just statistics. So, I would like to open the floor to questions if you guys have any.
This ton of data you have, you end up sort of going down a rabbit hole. And how far can you allow yourself to go down the rabbit hole before you begin to lose your tether to underlying chemical phenomenon and things you can observe in the...
Right, so that's a very good question. It is, you saw the one, we call it pair plot. It plots everything against another section of the data frame. We use that as like a guidance to say, hey, this might be something to work into, but we also use our chemical intuition to say, oh, well, of course, evaluation and outlier phi and psi angles are related. That's how you define what an outlier is. So it can spiral you down this path that could drive you crazy, but you know, it's important to know what to look for and what you can just say, oh, that's like obviously a trend we should see.
Okay, thanks for speaking again.